Thank you very much. Yes, so the title is Tropical Curve Counting, and I report on a joint work with Andres Jaramillo Puentes, Sabrina Pauli, and Felix Wörle. And the main purpose, outline of the talk is that I would like to show you how tropical geometry can be used as a tool in enumerative geometry. So in enumerative geometry, we fix our favorite geometric objects, in my case, mostly curves, and then we fix some conditions that we require the curves to satisfy, for example, to pass through certain points or something. And then we count how many of the objects actually satisfy the conditions. And of course, the conditions have to be picked in such a way that there is only a finite count and not like a higher dimensional family of objects satisfying the conditions. So here on this picture, you see a basic example. We have 4 points in the plane and a line, and we ask how many conics pass through these 4 points and are tangent to the line. And you can see from this picture that there are exactly 2. Yeah. Such enumerative problems have a long tradition. They even go back to questions from the ancient Greeks. But not all of them are that easy to answer, and that's something that I like about it. Often these problems are easy to pose, but not easy to answer. And so there's lots of connections also in other areas of mathematics, and a very fruitful area still nowadays. So now I'd like to introduce the main players of this talk, main enumerative problem for this talk. That's these numbers NC of D. That's the number of complex degree D rational plane curves that pass through 3D minus 1 points in general position. And an easy dimension count shows that 3D minus 1 points is exactly the right number of points to actually make this a finite count. Yeah. And in this table, you see some examples. So if D is 1, then we're asking for the number of lines that pass through 2 points. Okay, that one is easy. Obviously, there's just 1. The next entry, here we ask for the number of conics that pass through 5 points. Yeah, this is something that you could ask your students in a first class on algebraic geometry, because we're just having linear spaces that we intersect. The points give linear conditions, and the space of our conics is just a linear space. So, you know, it's just an intersection of linear spaces. It's also just 1. This entry asks for the number of rational cubics that pass through 8 points. Now this one is a little more difficult because now a general cubic is of course not rational. And so to be rational, you have to be on the discriminant locus inside the space of all cubics. Yeah? And you can compute that this discriminant locus is of degree 12. And then once again, you intersect with linear conditions, and then you actually have 12 cubics that pass through 8 points. Okay, now I will stop going through this table. I won't explain any further number. You just look at those numbers and you realize how quickly they actually grow. Yeah, and I believe that you won't be surprised when I tell you that many of those numbers were not known for quite a while. Yeah, only until d equaled 5, they were known until 1994. But then there was some influence from physics, actually from string theory and mirror symmetry, that inspired work by Kontsevich, who proved a recursive formula to compute all those numbers. And because we have this recursive formula now, we can actually compute those numbers. Okay, and just an example for another enumerative problem that is easy to pose, but not easy to answer, are the so-called characteristic numbers. These are numbers that count plane curves that satisfy point and tangency conditions. And for higher genus, these numbers are still not known. There's no recursive formula, there's no solution. So, you know, it's a reasonably easy question that one can ask, but we don't have a solution yet. There's still more work to be done in this field. Now, I would like to show you how tropical geometry can be used as a tool in enumerative geometry. What is tropical geometry? If you heard about it before, you may have heard about it as geometry over the Max-Planck semi-field. And as such, it has connections to computer science and optimization. But more important for this talk, it gives an efficient combinatorial tool to study degenerations. And that's how we're going to use it here. So you start with algebraic curves, and then there's some degeneration. that is called tropicalization, and outcome so-called tropical curves. And many of you know how this degeneration works, of course. For those of you who have not heard about it before, I'd like to ask you to just take it as a black box for the purpose of this talk. It's just some process that takes an algebraic curve and takes and outputs a tropical curve. Yeah? But what is a tropical curve? It's a weighted piecewise integer affine linear inverse graph in R2, satisfying the balancing condition. So I showed you some examples here. Let me explain how to understand those examples. So first of all, these graphs have unbounded edges called ends. Those are these edges. Yeah, they are supposed to go on forever. It's just that the iPad had some limit, so I couldn't continue drawing. Yeah. So these continue forever. These are the ends. Yeah. And besides that, we also have some bounded edges. Yeah. And it's an inverse graph. So this thing that we have here, that is actually like a crossing of two edges. Yeah, it's parameterized by an abstract graph, and those two edges only cross. There's not a vertex here. And then every edge is supposed to map on a line segment that has a rational slope. Yeah, and so it also has an integer direction vector pointing away from a vertex. And the balancing condition now says that the direction vectors that leave a vertex have to sum up to 0. So for example, for this vertex, we have this end pointing to the left, so -1, 0 is the direction. We have this diagonal end pointing diagonally upwards, 1, 1 is the direction. And we have this bounded edge that goes down, it has slope 0, -1, and those three vectors actually add up to 0. And that has to be satisfied for every vertex. Now, I did not yet explain what the weighted weighted means. These tropical curves, they come with an extra piece of data, which is a weight for every edge. And for the pictures I've drawn, almost all the edges have weight 1, and that I have not marked because this is sort of the trivial weight. Only in the second example here, this one edge, that has weight 2. Yeah, that's the little 2 that you can see here. And the weight goes into the balancing condition. If you sit at this vertex here and look around you, yeah, then you have this edge, which has slope -2, 1. Yeah, you can, if you don't believe it immediately, you can just follow. Yeah, this goes down 0, -1. This is 1, 1. And then this is 2 in this direction, 2, -1. The other direction, -1, 2. Yeah. And this goes down with 0, -1. And now we don't take the primitive vector in that direction. The primitive vector would be 1, 0, of course, but we multiply with the weight, then it is 2, 0, and then we sum up those three vectors, and once again, this is 0. So tropical curves are those weighted, piecewise integer affinely linear inverse graphs in the plane that satisfy the balancing condition. What does it mean for a tropical curve to be rational? It just means that we have to be parameterized by a rational graph. So both my pictures are rational curves, because once again, this here is just a crossing of two edges. So if you think of them as being apart, you can see that there's a rational graph abstractly that parameterizes this curve. And this one, you can immediately see it's a rational graph. So these are two rational curves. And what is the degree of a tropical curve? That is just the number of ends in those three special directions. And if you know more about the tropicalization process, then you know that those ends come from intersections with the toric boundary of the algebraic curve you started with. And so a degree D general algebraic curve in the plane always has D intersections with each of the boundary lines, and they produce those D ends. Yeah. Okay, so these two pictures that you can see here, these are both tropical cubics, because we always have three ends in those three directions. Yeah? So that's an example of two tropical cubics that you can see here. Okay, and once we know what tropical curves are, we can go and make the completely analogous definition to the definition we've seen before in the algebraic world. We want to count tropical curves satisfying point conditions. However, there's one slight thing I have to pay attention to. When I say count, I don't just mean count one by one. I count with some multiplicity. And this multiplicity happens because this degeneration is very much not injective. Many algebraic curves can tropicalize to one and the same tropical curve. And so when I want to count, I have to count one tropical curve with a multiplicity that reflects how many algebraic curves tropicalize to this one, yeah? And then I do that, yeah? So this multiplicity mult c of my tropical curve gamma, that is the number of complex curves tropicalizing to gamma. But the good news is that this number can be computed purely combinatorially. So I don't need to really understand this degeneration process and compute with this degeneration process, which would be a bit difficult. I can just look at the combinatorics of my tropical curve, and I can compute this multiplicity. And there's the famous correspondence theorem by Grisha Mihalkin from 2005, who proved that the number NC of D that we talked about before equals the tropical counterpart NC of D trop. Now, admittedly, if I phrase it like this, that the multiplicity is the number of complex curves tropicalizing to one tropical curve, then this theorem seems like no big deal because I sort of defined the tropical number to give me the right count, right? But the content of the theorem is actually the fact that you can compute this multiplicity so easily, yeah? That you don't have to know about this degeneration, that you can just take the information out from the combinatorics of your tropical curve. And this theorem sort of opened a door, yeah, because once you have this correspondence theorem, you can now use the tropical side to study the numbers that you actually care for, yeah. You can try to find new formulas, yeah, structural properties, whatever, by just looking at those nice graphs in the plane, and it's nice to use this combinatorial tool to get new information about your algebraic enumerative invariance. And just to mention one example, by Andreas Gartmann and myself, we gave a tropical proof of the recursion by Kontsevich. So that can also be shown with combinatorial methods. Okay, this picture shows you how this tropical curve counts actually works in action. Yeah, I have to explain this picture too. You should please imagine that those points that I've been drawing are always one and the same set of 8 points. Yeah, it doesn't quite look like that, but I'd like to ask you to look at this picture with some topological lenses. Yeah, so just pull a little bit some of those edges. It's actually hard to draw. Yeah, but if you just allow some of those edges to be pulled a little bit, I hope that you can see that you could arrange all those points to actually be the same points. Yeah. So let's imagine we have this set of 8 points, and this picture now shows all tropical rational cubics that pass through the points. Yeah. So they're all cubics. You can see that they all have 3 ends in the 3 direction. They're all rational. Yeah, I've always drawn these edges in such a way that you can see that it's actually a crossing. Yeah, so they're all rational. Yeah, and I hope you believe that these are actually all tropical curves that pass, all tropical rational cubics that pass through these points. Now let's talk about the multiplicity. So it turns out that for all those curves here, the multiplicity is just 1. Only for the last curve, this has complex multiplicity 4. And so altogether, we have 8 times 1 plus 1 times 4, which is our 12. Yeah, so this is the tropical way to recover this number 12. That in this case we knew before already, sure, but just so that you see an example how you can compute this number with tropical methods. Okay, now we want to switch gears a little and talk about real enumerative geometry. So we take real curves, meaning plane curves, which are defined by a real polynomial. Yeah. Now, the bad news is that if I just try to do the analogous problem, so I take degree D rational real curves passing through real points in the plane, then this number is sadly not an invariant. For example, there can be 8, 10, or 12 rational real cubics through 8 points, depending on how precisely you picked your points. This goes back to Kalamov. Of course, as enumerative geometrists, we are not really happy if we don't have an invariant. We're much happier if something does not depend on something like the choice of point conditions, right? And luckily, Valgeorges came to our aid, Jean-Yves Valgeorges. He proved in 2005 that you can, instead of just counting those real curves of the real rational curves of degree D, you can count with a sign. You can take a sign count, yeah? And the sign depends on the geometry of the curve, yeah? So if you take general point conditions and then a rational curve through them, then the curve will have some nodes, yeah? And in the real numbers, local pictures of the nodes are either like that, yeah, when the local equation is of the form x squared minus y squared equals 0. So it splits into two factors, two real lines that actually cross, yeah? Or you can have a local equation of the form x squared plus y squared equals 0. Then over the reals, of course, it has only that one solution, the point 0, 0, yeah? Over the complex numbers, so there's sort of two complex conjugate lines hidden in the complex world that you don't see if you look at the real picture, yeah? So over the reals, this is what we call a solitary node. And we count our curves with the sign -1 to the number of solitary nodes. And Plenary proved that if you do this, then you actually get an invariant. So the NR of D, which is just a variant of the counting problem I introduced for the complex numbers, that is the sign count of real rational degree D plane curves through 3D -1 real points. Yeah. Okay, now you might wonder, how reasonable is it to just count with signs? What is that good for if I'm actually interested in counting curves, right? But the answer is this NR of D. Well, first of all, it's a lower bound for the total number of real curves, obviously, right? Now, this is maybe still not very convincing, because if this lower bound was negative for 0, then this is not a big deal, right? But the good news is it isn't. Yeah, you can show, and actually with tropical methods, that it's asymptotically logarithmically equivalent to the number of complex curves. So those Valger invariants are actually big, and this lower bound is actually a very good lower bound to know, and it's an invariant. So it's really good to have this Valger invariant. And the statement with the asymptotic log equivalence, that was proved by Edenberg, Kalamov, and Schustin, as I said already with tropical methods. If we have a real polynomial defining our real curve, and we insert some point defined over the complex numbers, such that f of p vanishes, then f of the complex conjugate will also vanish, just because the coefficients of the polynomial are real. That means that I can as well impose pairs of complex conjugate point conditions. Yeah, in that problem that I talked about earlier, I had only real points. But now instead of having only real points, I also want to allow pairs of complex conjugate points. And if you want, you can then think of that real curve rather as, well, you sort of take the whole complex solution set, but it comes with the conjugation, of course, and the fixed locus. That is the real part. That is what I earlier called the real curve. But the whole data of the complex part and the conjugation actually comes along, right? So you can think of that as the real curve. And if you have that picture in mind, then I think it makes a lot of sense to fix, yeah, pairs of complex point conditions, not only real points. So let's fix S pairs of complex conjugate point conditions and R real point conditions, such that the dimension count has to be satisfied again. So R plus 2S has to be equal to 3D minus 1. And then Valger also told us that the corresponding number NR of ds that counts now the degree D rational real curves that satisfy those point conditions with the sign, yeah, and the same sign we talked about before, the -1 to the number of solitary nodes. This number is also an invariant. That was also shown by Valger. And there's a correspondence theorem also by Krisha-Mihalkin that says, first of all, let's go back to the numbers NR of D, where we don't have complex conjugate points, only real points. And then those numbers NR of D can be computed by tropical means again. I can just count one and the same set of tropical curves. It's only the multiplicity that I have to change. Yeah. So let me show you a picture. Yeah, let's go here and then show you the picture first. And you see that it's actually the same picture I showed you before. Yeah, before I had the headline NC of 3 is 12. Now it has the headline NR of 3 is 8. But it's the same tropical curves that I count, the same tropical cubics through those 8 points. Just the multiplicity has to be adapted to this real world now. And the multiplicity, it was 1 for all of those curves. This still is 1. And this one, which had multiplicity 4, that is 0 now. Yeah. very roughly, you can think of the real multiplicity as the complex multiplicity mod 4. That means you can show that a multiplicity which is congruent to 2 mod 4 will never show up. If you're congruent to 1 mod 4, you'll stay 1. If you're congruent to 3 mod 4, you'll get a -1. And if you're congruent to 4 mod 4 to 0, you get 0. Yeah. So in this sense, the real multiplicity is actually easy to deduce from the complex multiplicity. And the way to think about that is that this tropicalization process, that doesn't really know about the ground field. Yeah, the combinatorial objects that come out, they don't really know which ground field you fix. It's just going to be the same combinatorial objects. Only when you go backwards, sort of, when you ask yourself questions like, how many of my objects tropicalize to this one? Then the question which field you were working on is suddenly important. And then you have to take this into account. Yeah. For these more general numbers that are introduced, the NR of ds, that count degree d rational plane curves, real curves that pass through S pairs of complex conjugate points and only real points else. Also for those numbers, we have a correspondence theorem. This is by Schustin. And well, it just says, once again, there's an analogous tropical count that I call NR trop of ds. And the two counts are equal, so you can count your enumerative invariants with tropical methods. It is just that those tropical curves are combinatorially quite a bit more involved than the ones that I showed you. Now, when I change the point conditions to complex conjugate point conditions, the pictures will actually be different. The reason is that complex conjugate points tropicalize to the same point. Yeah, and so it doesn't look like 8 different points. It looks like, well, sort of thick point conditions. We like to draw them as thick points, which sort of impose 2 conditions and the normal points. And then the tropical curves have to follow along with that. And the combinatorics is just going to be more involved. But still, it is possible to compute those numbers with combinatorial methods. And I'll go back to this and show you a picture, but only later after we talked about more general versions of such curve counts. Okay, this example we already looked at. Yeah, so now we're going to be quite a bit more ambitious. Why do we stop at complex numbers, real numbers? Let's take any field, yeah, and let's ask similar counting problems over arbitrary fields. And this is a research direction which has been developing recently, since the last 10, 15 years maybe. People call it the quadratic enrichment of enumerative geometry. And it has been started by people like Jesse Katz, Kirsten Wickelgren, Mark Levin, and many others. And the idea is that we want to make methods from algebraic topology available for algebraic geometry. This is called A1 homotopy theory. And then we can compute so-called quadratically enriched degrees that actually count something. Yeah? And what does it mean, this quadratically enrichment? Also in this world, I don't seriously count one by one. I count with some multiplicity, and the multiplicity is going to be an element in the Grothendieck Wittring. Now, what is the Grothendieck Wittring? It depends on the field, ground field K that I picked. Oopsie, I lost the mouse. Here it is. So Grothendieck Witt of little k. It contains all formal sums of isomorphism classes of quadratic forms from a vector space over K to K. Yeah, just quadratic forms from V to V, V times V to K. After we fix the basis for our vector space, we can just think of a matrix roughly. Yeah, so we have a vector X in coordinates now after fixing the basis and Y in coordinates. And then the quadratic form will send this tuple xy to X transpose times a matrix times Y. Yeah. So in some sense, you can just think of matrices. Yeah. But I said I want only isomorphism classes of quadratic forms. Yeah. And that means that, for example, this matrix 1, 0, 0, -1 will be equivalent to 1, 0, 0, 1 when I'm working over the complex numbers, right? Because when I do a base change for quadratic form, I have to multiply from left and right, one with a transpose, but this diagonal matrix doesn't matter, right? And I can pick this basis change 1, 0, 0, I, yeah, multiply it from left and right, and then I get out of my matrix 1, 0, 0, minus 1, the matrix 1, 0, 0, 1, yeah? So over the complex numbers, these two matrices are equivalent, but over the real numbers, of course, they are not, yeah? Because I had to use the imaginary unit I here. There was no other way to base change from one to the other. So over R, these two are not equivalent, but over C, they are. That already gives you a hint that this Grothendieck-Witt ring actually depends on the ground field we're talking about. And if you think back of your linear algebra studies, where you classified normal forms for quadratic, for matrices representing quadratic forms, then I'm sure you remember that over the complex numbers, you can always fix a basis in such a way that you only have to have some ones on the diagonal, yeah? So the rank of your quadratic forms, all that you need to know, only number of ones that counts, only the rank. Whereas over the reals, you need the rank and the signature, because over the reals, the quadratic form can have some ones and some minus ones, and it's important to know how many ones and how many minus ones to really know the quadratic form. Yeah? And so, you know, if we think about the complex numbers and think about just the rank, yeah, then this is very close to counting something. Whereas if we think about the real numbers and think about the signature, then this is very close to something like a sign count, like Belgeauger defined for us. Yeah? And this is how you can see, how you can motivate, hopefully, that this Grothendieck-Witt ring will give you a way to simultaneously treat such counting problems that we talked about earlier. Okay, some more information about Grothendieck-Witt of K. So I told you it's a ring, and it contains all formal sums of isomorphism classes of quadratic forms. And the sums I can just think of as direct sums of the vector spaces. And for the ring structure, I also need some multiplication. And the product is just coming from the tensor product of vector spaces. And then I can complete this to actually get a ring structure. Now this GW of K is generated by elements that look like this, yeah, brackets A. For an element A in K star modulo K star square, and this symbol stands for the quadratic form that goes from K times K to K, and sends, in this case, two numbers, X and Y, to just the product, X, A, Y. Or put differently, you can just think the 1 by 1 matrix that has the element A as entry, yeah? And then I said I want to have my A in K star modulo K star square. This is just because of basis exchange, right? Because if I pick a different basis for my one-dimensional vector space here, that's like multiplying with some factor b, yeah? But then in the quadratic form, that b will show up with a square, of course, yeah? I have ab squared, doesn't matter, it's just a field, right? And so I only need to know what A is up to such squares, yeah? So A only from K star modulo K star squared. And then it's generated by these symbols, by these, you know, 1 by 1 matrices, and they satisfy some relations. A plus B is A plus B plus AB, A plus B. A times B is AB, and A plus minus A is 1 plus minus 1. And as I said already, plus you can think of as direct sum. So you can also think of this as this matrix that we've seen before, 1, 0, 0, minus 1. And it plays a special role, so it gets an extra name. It's called the hyperbolic form. Okay, and two concrete examples. GW of C is just Z because it's only the rank that counts. Yeah, there's just one generator, bracket 1, yeah, and I just need to know how many bracket 1s I have. And it's formal sum, so negatives are also okay, yeah, but I just have that one generator, bracket 1. And GW of R, that's C adjoined the group with two elements, because for R star over R star squared is just plus or minus 1, yeah? I'm a square over the reals, sorry, yeah. So I can either be a square or not, yeah? Either 1 or minus 1. That's this. And so this GW of R is generated by bracket 1 and bracket minus 1. And so I can write it as Z adjoin the group with 2 elements. Okay. Sorry. Okay. So now Mark Levin studied generalization of the curve counts that we talked about earlier. He defined this number, NA1 of D. And as I said, when we're not seriously counting, we're adding up multiplicities here. So it's a sum over all algebraic curves that go through my points. So I have some points that I fixed, that I defined over K, yeah? But then the algebraic curves, I look at the solutions for my counting problems. I do not necessarily require them to live over K. They can live over some field extension, yeah? But they still have to pass through those points, yeah? A little bit like those complex curves that I looked at earlier that pass, well, real or complex curves that pass through the complex conjugate points, yeah? That I have a bigger solution for my curve, yeah? And then the multiplicity with which I count my curves is in brackets a number. This number is the arithmetic multiplicity of my curve. And put roughly, it's the product over all nodes of the curve, and then bracket the determinant of the Hessian of my curve at this point. But when I say it like this, I'm cheating a little bit because the curve doesn't need to be defined over little k, and so the nodes don't need to be defined over little k as well. And then I have to use a trace to get down to GW of little k. Yeah, so this element a priori would live in GW of big K, but I trace it down and then it lives in GW of little k. And then I have this whole sum that lives in GW of little k. Okay, and the content of the theorem is now that that is an invariant. That is once again an enumerative invariant. And I should point out, because it's not clear from the notation, this guy depends on the ground field, little k. Yeah, that is sort of hidden in the notation here because it's this, what I get out is an element in GW of little k, so it depends on the ground field. Yeah, and I claim now that this enumerative invariant simultaneously knows about the invariants we talked before. Yeah, how does that work? Well, let's just specialize our ground field, let's say, to the complex numbers. Yeah, then, well, I don't need any field extensions here. Yeah, all my curves will be defined over C that pass through these points over C. And then, you know, whatever you compute here for the nodes, GW of C is only generated by bracket 1. Yeah, so you'll get down to just summing up bracket 1s. And so we're just talking about a count. We're just summing up 1s for each of the complex curves. Yeah. If we specialize to the reals now, the situation is a little bit different. So for sure, we have some solutions which are real curves. And these are the ones that I talked to you before. And then I think that it's not so hard to believe that this bracket, this quadratically enriched multiplicity will be -1 in case for solitary nodes and +1 for other nodes, just like the Valgeauger sign is defined. Yeah. So this thing is going to be equal to the Valgeauger sign for a real curve. Now, the only thing to pay attention to is that in this situation, I also sum over more curves. I also sum over complex curves that pass through real points potentially, but then those will come in pairs. They will always come in complex conjugate pairs, and it turns out that their contribution always cancels each other. And for that reason, if I go and take this invariant and specialize little k equal to r, then I get back my Valgeauger invariant. And this is something that I find extremely nice about those new arithmetic enumerative invariants, that they encompass so much information. Yeah, you just specialize to your favorite ground field, and yeah, it's all contained in here. You have all this information about the enumerative numbers simultaneously. That's something that I find really very impressive, I must say. Okay, and then also here we have a correspondence theory by Andres Jaramillo-Puentes and Sabrina Pauli, who showed that you can compute this quadratically enriched count in the tropical world. And once again, we're just counting one and the same set of tropical curves. We only have to count them now with quadratically enriched multiplicity. Yeah. How does that look like? Here's my favorite example again, the count of tropical cubics, rational cubics, through 8 points. All of those will have multiplicity just bracket 1. And this guy has multiplicity 2h. H, the hyperbolic form, the 1, 0, 0, -1 matrix. Yeah. And so the whole arithmetic count of cubics is 8 times 1 plus 2 times the hyperbolic form. And now let's repeat the specialization again, just to see how it happens in this situation. Yeah. Let's specialize to the complex numbers. Then, okay, the hyperbolic form is just a 2 by 2 matrix, so the rank is 2. Yeah. So 2 times 2, 2 times 2 plus 8, that gives you the 12 that we had over the complex numbers. If we specialize to the reals, on the other hand, there, we have to pay attention to the signature. So the hyperbolic form will cancel out. 1 and -1 will just give 0. So this summand will just contribute nothing. And here you have your 8 ones. So if you specialize to the reals, you get your 8, which was the Bell-Daudet invariant in this situation. And once again, it's just the same set of tropical curves we're talking about, only the multiplicity we have to adapt. Okay, now similarly to how we discussed that real curves can also pass through complex conjugate points, also here I can be even more ambitious, right? Who requires me to fix only points which are defined over k? Nobody. I could fix arbitrary points, yeah? And what we want to do here is we want to fix S pairs of conjugate points in quadratic field extensions, little k in k adjoint some square root. And then furthermore, R points, which are defined over the ground field k. And then still 2S plus R has to sum up to 3D minus 1, of course. And then I can count, again, degree D rational plane curves that satisfy those point conditions with their arithmetic multiplicity. And this is also an invariant, and this was proved by Jesse Katz, Mark Levin, Jake Solomon, and Kirsten Wickelken just recently. And it's a very nice result because this is once again a really nice class of enumerative invariants, which works for any field. Yeah, so it has a lot of information. And in particular, we can imagine that we specialize to the ground field R, and that we fix, oopsie, what did I do now? Sorry. Yeah. And that we fix square root of -1, yeah, and then we have R and C as our field extensions here. And then those conjugate points that I'm talking about are just complex conjugate points as before, yeah? And so this invariant specializes to this NR of ds that Bell-Daudet introduced earlier, yeah? And in the same way, the sign will be the same sign, and it really specializes to that enumerative invariant. Okay, so they proved this really nice theorem. And then, Andres, Sabrina, Felix, and me started thinking about, okay, how can we actually compute those numbers? And I think it's pretty obvious that tropical geometry suggests itself, or at least to me, it was. In my case, I thought, okay, let's use tropical geometry to compute those numbers. And the trouble that I already mentioned earlier with the complex conjugate points in the real situation is that conjugate points tropicalize to the same point. Yeah? And that means that the combinatorics now is just going to be more involved. Here's a picture. I have to explain this picture. So these curves that only pass through thin points, these are the 9 rational tropical cubics we've seen before that pass through my fixed 8 points. Yeah, these are those 9 tropical rational cubics. And now I want to go and just merge pairs of points into one point that I then draw as a thick point to keep this information that it came from 2 points. Yeah? So let's do this. Let's take those 2 points and merge them, and those 2 points and merge them, and those 2 points, merge them, and those 2 points. And I hope that you see that what comes out is this picture. Now one should know again how to read this picture. Here I've drawn a double edge. Yeah, this double edge, of course, those two, I mean, if you merge those 2 points, those 2 edges will just land on the same line. Yeah, so it's just twice the same line. But just to keep in mind that there were 2 of them, I draw them like double edges here. If you want, you can think that I'm trying to draw the parametrizing graph with the picture, actually. Yeah. Okay, so, merging points from this curve gives us this guy. Let's take the next one. Let's merge points, those two, those two, those two, and those two. Then we get this picture here. Let's merge points here, those two, those two, those two, and those two. That's this picture here. Let's merge again, those two, those two, those two, and those two. That is again that picture, not a new picture. That picture again, right? Let's merge here, those two, those two, those two, and those two. That is again this picture, not a new picture. Okay, if we merge here, we end up with this picture. If we merge those, we end up with this picture, where we now even have whole sub parts of the tropical curve that are sort of doubled, because we merged those pairs of points. And if we merge for this, again, same picture. If we merge for this, finally, this picture. And now I'm sure you'll believe me that I can give a definition of how these tropical curves that pass through such double points look like, But I want to actually spare you the technical details, and I hope that this picture is just good enough to give you an idea. And what you should take away definitely is they are more complicated than the ones we looked at before. The ones we looked at before, they only had 3 valent vertices, and now we suddenly have those funny 2 valent vertices. We also have these crossings with a point on them. So combinatorially is just a whole new chapter somehow, but it's still manageable. So with Andres Jaramillo Puentes, Sabrina Pauli, Felix Röhle, we proved our correspondence theorem that states you can compute those quadratically enriched enumerative invariants that count curves that satisfy conjugate point conditions and k-rational point conditions. You can compute those by counting the suitable tropical curves. When I call it a correspondence theorem, I'm exaggerating a little bit because we actually only proved it for a particularly point configuration or a set of point configurations. But that is good enough to give you actually a tropical algorithm to compute those numbers. And here's an example. So let's discuss NA1 of degree 3 and then up to 4 squares that I can attach to my fields to consider complex, not complex, to consider conjugate points in this quadratic extensions. And the pictures we just saw, these are the pictures that came out of the cubics that we discussed before by merging points. So these are the pictures we have to count, and we count them with their quadratically enriched multiplicity. And I just wrote this quadratically enriched multiplicity underneath all those pictures. And then you can sum those up, and this is your invariant. And just to stress this, what I really like about this invariant is that it knows everything. And I seriously mean everything at this point. So we can go and insert, for example, for our ground field, the complex numbers. Once again, this number, of course, depends on the choice of the ground field because it's an element that lives in GW of K, which depends on K. Let's specialize to the complex numbers. Over the complex numbers, only the rank counts. So those 2's, bracket 2's, are as good as bracket 1's because square root of 2 is in C. I can get rid of that. I just add up the rank and I get my 12. Okay. I could also insert K equal little r, and then I could still let all my di's be 1. Square root of 1 already lives in R, meaning I'm not really extending my field, meaning I only have real points at the moment, just in the original Verger problem that I discussed. And then let's look at that. So all di's are 1 now. Over the reals also, 2 is as good as 1. So we have 2 1's, another 2 1's, and another 4 1's. And then the h, of course, specializes to 0 again, because 1, 0, 0 minus 1, the signature is 0. So I have my 8, which is my Verger invariant that I discussed before. But now I can do even more. I can insert the real numbers. And let's say I let one of my di's, d1, to be minus 1. Then for that one pair, I'm talking about one pair of complex conjugate point conditions, because I'm talking about the field extension R in R adjoint square root of minus 1, meaning C. So I have a pair of complex conjugate point conditions. And other than that, I have only real points. And when you set one of those di's equal to -1, then one of those 2's together with that -2 will be the hyperbolic form again, which specializes to 0. And the other ones are just 2's which are 1's. So I add the rest up and I get to 6. Yeah? I can continue. Now I can also let 2 of those d's be -1. Yeah? And then another of those 2 di's will become a -2 that cancels with one of those 2's. Yeah? And so I'm down to 4 now. And I can continue further. Then there's more cancellation. If I let 3 of the di's be -1, 3 pairs of conjugate points, yeah, then I have the invariant, which is just 2. And if I set all the di's to -1, then in that special case, the Belgian invariant is actually 0. Yeah? So if I have 4 pairs of complex conjugate points and discuss the real curves through them with Belgian sign, that is just 0. And this one expression here, that knows all of those numbers. Yeah, it's a simultaneous way to describe all those counting problems, which I really find very nice. Okay, now I would like to give you a very rough overview of the proof of correspondence theorems. And what I'd like to do is to sort of point you to the challenge that had to be solved in each of the cases. Yeah. So the combinatorics of the tropical curves gives me a toric degeneration of the plane. And every vertex of the tropical curve, there's just a local picture, just one vertex, corresponds to a little toric surface in this degeneration. And then I sort of have smaller counting problems to solve. I solve small counting problems in these toric surfaces. An edge of my tropical curve, like here, yeah, local picture again, an edge connecting 2 vertices, that corresponds to 2 toric surfaces. And that gives me some cluing conditions because the contacts with the toric boundary of the solutions in the 2 toric surfaces, that has to match to give me one global solution in my degenerate situation. Yeah? Then, of course, you have to show that every such degenerate solution comes from an honest solution. And there's some work hidden here, but it's just a rough overview. So we're sort of patchworking solutions. This is going back to Viro. We're patchworking solutions to the counting problem from such small pieces whose combinatorics is governed by the tropical curve. And then if we prove the correspondence theorem over C, the question we have to answer is, how many solutions do we have? Yeah, that's it. How many solutions? I'm not saying it's easy, but that's it. Yeah. If we prove the statement over R, then it's not only how many solutions, it's which of those solutions are real and what is their Belgeauge sign. So I must know their nodes, which of their nodes are solitary and which not. Yeah. If I prove the theorem over K, what Anders and Sabrina have done, then it's find all solutions over any extension of my field little k, all their nodes, and compute the arithmetic multiplicity of all the nodes. Yeah? So I hope that you can see that there's quite a different challenge. Even though they're all versions of correspondence theorem, they're quite different, and you have to solve different questions in each of the versions. And now in our version, unfortunately, I cannot really point you to one challenge that had to be solved to get to our version, because the trouble is that just every step is somehow more involved. Yeah? And that starts with the combinatorics. The combinatorics was more involved. We discussed it, 4-valent vertices, funny crossings with points, and so on. And with the combinatorics being more involved, you have a much bigger classification of those little pieces that you need to clue. And for each little piece, also, just the fact that the point conditions are not defined over K, but over those quadratic conditions, make it more complicated to actually compute the solutions. Yeah. So in some sense, there's not that one challenge that I can point you to, but just every step is a mess. Yeah. It took us a while, took us some nerves, but yeah, I'm quite happy that it worked out and that now with tropical methods, we can compute all those numbers simultaneously. And with that, I'd like to end. Thanks for your attention.
Questions? Were you able to find like a conservative like recursion for this more general, quadratic enhanced counting?
No. So the reason is that if we prove the tropical Kontsevich formula, then a very important step is to interpret this multiplicity in a way that is governed from tropical intersection theory. And that doesn't work over the reals. We tried that actually ages ago when Verger proved his theorem. We tried to also understand tropical versions of some conceived recursion over the reals, and that tropical intersection interpretation just doesn't work. And that now, I mean, that doesn't immediately stop me, because sometimes when you look broader, you see more, right? So I view this quadratically enriched count now as a new chance to maybe understand in which sense the tropical intersection product interpretation could still work. But this is far from being answered. So at the moment, no, and there is some serious obstruction, but maybe in a few years.
Is there a Markwig with version of conical mullet? I mean,
not that I know of. I don't know. No, I don't think so. No, yeah. And the problem is precisely that, I believe.
Yeah, so is there, where did these A1 multiplicities actually live? Because you defined it where you fix a field K. There seems to be a universal Markwig, the group in which they live.
Well, they live in GW of K, whatever your K is, yeah. And that is an object that you can write down. But to really know what it is, you have to know what K is. So. But this invariance
should be a algebraic object in which they live that sort of a functor that when you plug in, okay.
Well, yeah, it's GW of K. So I could complete this phrase here by element GW of K. Yeah. Does that help? Or
just because the formulas are the same for every case, so it's suggesting there should be some other formulation. But anyway, it's fine. I mean, it's clear what we're saying.
That's okay. Sorry, I don't think that time.
Have there been approaches to the percentages formula that are not tropical for this third count?
Sorry, I didn't quite hear. Has there been?
So it is similar to Domi's question. So have there been approaches to, or like attempts to prove percentages formula that are not tropical?
In the A1 world, I don't think so. And actually, I really think that the tropical reflection of the counting problem tells you what the problem is. There are initiatives where people try to compute those numbers, of course. One idea is to use wall crossing formulas in the sense that you want to change the surface that you live in by going up and living. So this actually works for arbitrary toric delta surfaces, not only in P2. So those wall crossing formulas is something you could use. Yeah, there are also other ways. So Kirsten Wickelgren and Erhan Budali, they are working on finding other ways to compute those numbers, but not with a conceived recursion. This at the moment is not yet possible. I think for that we really have to understand more about the connection to the intersection field.
Thank you.